Okay, so you've got 300 ohm resistors and a 3 volt battery connected as shown in this circuit diagram. In part A, we want to draw an arrow next to resistor 1 in the direction of the current. And we know that the current flows out of the positive terminal of the battery and around the circuit. So when it goes to R1, it's going in the downward direction. And then when it gets to this point, it's going to split. So some of the current is going to go this way down through R2, and some will go this way down through R3. But in part B, the question says to draw the arrow representing the direction of the average velocity of one of the electrons. Current doesn't actually flow in this direction around the circuit. It's actually the negatively charged electrons that flow in the opposite direction. That's just the equivalent of current flowing in that original direction. So even though the current in R2 is defined as going in the downward direction, the actual electrons are moving through R2 in the upward direction. And then in part C, we just want to draw a ammeter and a voltmeter properly connected in the circuit so that it measures the current and the potential difference in resistor R3. So the way that would look is the ammeter would have to be connected in series. So it's just got to be somewhere in this branch just right here. It cannot be up in this region because that would be the current through R1, and it can't be over here, obviously. So ideally, we'd want to erase, or I guess technically white out part of the diagram to put an ammeter in there, but I think it's fine if you just kind of draw it over top of the diagram like this. So that's going to be a circle with an A in it, so that whatever current is flowing through this resistor, that same current will also flow through that ammeter. And then for the voltmeter, it needs to be connected in parallel. So for that one, you need to connect something directly above the resistor and directly below the resistor. So it might have a part coming off here, and then that's going to be a circle with a V in it. And I'm going off the edge of the screen here, but that's what that's supposed to look like. So it's like an extra part of the circuit we're adding on, connected across resistor R3. Alright, in part D, we want to calculate the amount of current that flows through the battery. So to do this, we're going to have to first figure out the equivalent resistance of the entire circuit. We have two resistors that are in parallel, so we can do the parallel combination, which is add the reciprocals together. 1 over 100 plus 1 over 100. They already have the common denominator, so it's 2 over 100, or 1 over 50. And then we've got to take the reciprocal of that, so it's 50. So the equivalent combination of those two resistors in parallel is 50 ohms. A quick piece of advice that would simplify some time on a test is that whenever you have two resistors in parallel that are exactly the same, the equivalent resistance of both of those will always be half as much as the resistance. You see in this case it was 100 ohms for each one, so the equivalent resistance is 50 ohms. So if I redraw this circuit, it now looks like this. You've got resistor R1, which is still 100 ohms, and then those two in parallel are combined. We'll call this R23, and that's equal to 50 ohms. And now you can see that these two resistors are in series, so you would just add them together. So that means the equivalent resistance of the entire circuit, we call it R equivalent, or you might also sometimes see it referred to as R total, or you might also see it referred to as just R123, because it's those three resistors combined. However it's put is going to be equal to 150 ohms. And now you can get the current flowing out of the battery using Ohm's law. I is equal to delta V over R. It's going to be 3 over 150, which will simplify down to 1 over 50, or 0.02 amps for part D. In part E, we want to calculate the numerical values of the current and potential difference for each of the three resistors. The easiest way to do this, since we're calculating a whole bunch of numbers, is just set up the VIR chart. And we've already done part of the math with the VIR chart. So we have, let's see, R1, R2, R3, and the total. We know that each resistor is 100 ohms, and we know the total resistance of the circuit, which we did down here was 150 ohms. The total voltage of the battery was 3, and we just calculated the current coming out of the battery, 3 divided by 150, which was 0.02 amps. Now, since that's the current that is flowing out of the battery, that current is going around here, and it's the same current that's flowing through R1, since it had nowhere else to go in the circuit. Remember making the analogy with the pipes that we talked about this past Monday? If this was pipes with water flowing and there was no way for the water to leak out of it, whatever water is flowing out of this battery is going to flow around here, and it's going to flow through this resistor. So the current in resistor 1 would be 0.02 amps. Now we can figure out the potential difference across that resistor just by using Ohm's law and multiplying 0.02 times 100. That would give you 2 volts. Since we now have 2 volts across this resistor, and there was 3 volts total, that means there's going to be 1 volt left, and it's going to be 1 volt across each of those 2 resistors. So we can say a 1 and a 1. And then you can just calculate the current, dividing 1 by 100, and you get 0.01 for both of those, which should make sense because that current, the 0.02 amps, was split evenly along those 2 branches. And that's 0.02 cut in half gives you 0.01 along each branch. Okay, in part F on the back, we're going to remove R1 from the circuit and leave the branch open. So if you removed R1, that would just create a gap in the circuit. It doesn't even make a loop with the battery, so no current would flow at all in this circuit. Even though R2 and R3 still form a loop together, if you imagine there's a gap right here, nothing can flow to the battery. So we can say that for F1 and F2, everything just drops down to 0. There's no current at all in that circuit. In part G, we're going to put R1 back in, and this time we're going to remove R3 from the circuit. So that still leaves a circuit intact with the battery, because we have the battery that goes through R1, and then that goes through R2, and then back to the battery. The R3 is just over here. It's just a gap in the circuit now, so it's almost as if that doesn't even exist. So you really don't even need to include that on there. You could just have it, the new circuit diagram, look just like this. And those are just 2 resistors in series. So we would just add them together. Since they're in series, that gives you an equivalent resistance of 200 ohms. Remember what we said on a previous assignment is that if you remove a resistor that's in parallel, because parallel resistors have a lower resistance, if you remove a parallel resistor, it's going to increase the resistance, which it has. We went from 150 up to 200. So with increased resistance, that means we're going to have decreased current flowing out of the battery, so there's going to be decreased current through R1. It was 0.02 amps originally, now it's going to be something less, but at the same time, since all the current is now flowing through R2, since none of it can go on this side, we're going to have increased current through R2. So you're going to find that this number goes down when we calculate it for here, and this number, the current through R2, is going to go up when we calculate it. It says quantitatively describes, that means we actually do have to calculate it. So we can do that real quick by just saying that the current is equal to, using Ohm's law, delta V over R. The delta V was 3. The equivalent resistance was 200. 3 divided by 200 gives you 0.15 amps. And now you can easily figure out the potential difference across both those resistors, since you know the current through them and you know the resistance of each one. So just use Ohm's law to solve for the delta V. And finally, in part H, we're going to now connect the 2 ends of the open branch with a wire, which is called a short circuit. And the reason it's called that is because if I take a wire and just connect it from, say, here straight down to here, get rid of this 200 right over here, since there's no resistance at all in that wire, all of the current in the entire circuit that comes out of the battery is going to flow along that path, and nothing's going to flow along this path. since this has zero resistance. So since all the current flows along this path, it creates what's called a short circuit, which means that it's as if this resistor is not even there. So we're just going to get rid of that whole branch of the circuit. So now we have a very simple circuit that just has the battery connected to essentially just one resistor. So you can now easily calculate the current that comes out of the battery. Just use Ohm's law, the 3 divided by 100. That's your current. And you can get the potential difference across that resistor. And there's going to be no current and no potential difference across R2, since all of the current is flowing along that wire.